Hello and Assalamu alaikum. My name is Muhammad Sabiul Hassan and I along with my group members will be presenting on non-comparison based sorting algorithms for our final project for the course Algorithms, Design and Analysis at Habib University. The sorting algorithms we have covered in our course can sort a structure that comprises of strings or integers after comparing each value with another value. This is usually followed by rearranging of those values in the data structure. However, is another approach where you can also sort or arrange items without comparing them with each other. There are some sorting algorithms that perform sorting without comparing the elements, rather by making a certain assumption about the data that they are going to sort. The process is known as non-comparison sorting, and the algorithms are known as non-comparison based sorting algorithms. For our project, we have decided to study three different types of non-comparison based sorting algorithms. The first one is a counting sort, which sorts using key values of data structure. The second one is the Radix sort, which examines the individual bits of keys. And the third is a bucket sort, which examines keys based on buckets. They are also known as linear sorting algorithms because they sort in O of n time. They make certain assumptions about data, hence they do not need to go through a comparison decision tree. In comparison-based algorithms, a comparator is required to compare values or items. Basically, this comparator defines the ordering, such as the numerical order, the lexicographical order, which is also known as the dictionary order, to arrange elements. On the other hand, the non-comparison based sorting algorithms don't use comparison, but rely on integer arithmetic on keys. Now, now, the question is, why did we decide to study on non-comparison based sorting algorithms? If you look at the performance of comparison based sorting algorithms, we realize that bubble sort, selection sort, insertion sort takes around of n square time to sort n items. Similarly, heap sort, quick sort, and merge sort takes around of n log n time on their best case and around of n square on their worst case. It can be proven that comparison-based sorting algorithms will take at least of n log n operations to sort n elements. Hence, you need a non-comparison-based sorting algorithm which allows you to sort elements in linear time. Now discussing our counting sort. Counting sort is a sorting technique based on keys between a specific range. It works by counting the number of objects having distinct key values, kind of a hashing, then doing some arithmetic to calculate the position of each object in the output sequence. The special conditions required for this counting sort are: number one, the values to be sorted must be integers in some range from minimum to maximum. We can call this the number of values in the range k. Number two, the total number of elements in the data structure must be greater than or equal to the range k. Here's a stepwise implementation of how the count sort works. In step 1, we store the count of each unique object that is present in a set in another set. Step 2, we modify the set such that the element at each index store the sum of the values at the previous index. Step 3, we output each object from the new set, followed by decreasing its count by 1. Let's look over an example of how an array is sorted using count sort.
Our first step will be counting the number of occurrences of each number. So, for example, 0 comes 1 time, 1 comes 2 time, 2 comes 1 time, and 3 comes 2 time. Then, the second step will be adding each number to the next number accumulatively. So, first number will come as it is, second number will become 3, the third number will become 4, and 6. The third step will be shifting each step to the right by one cell. So this one comes here, this 3 comes here, this 4 comes here, and here it is 0. To sort this array, we'll look at this table. The first number is 2. We'll check the corresponding index of 2 here, which is 3. So on the third index, we'll insert 2. We'll also add 1 to this number, so this will become 4. The next number is 3, so we'll look at the corresponding index, which is 4, and then we'll add 1 here. We'll repeat the process for all these numbers. Now our array is sorted.
We have implemented a counting sort algorithm using Python. We're going to execute this algorithm for this list and see the result. The list even contained negative integers and it is sorted. Here, this algorithm will help us to visualize the performance of our algorithm for variable size of n, where n is the size of our list. As you can see, for 1,000 elements or for n with a size of n, you can see the relationship is quite linear. Here's a snippet of our Python code. The time complexity of the algorithm is given below. In all the above cases, the complexity is the same because no matter how the elements are placed in the array, the algorithm goes through n plus k times. There are no comparison between elements, so it's better than comparison-based sorting algorithms. The complexity is O of n plus k. As you can see that in the Python code, the number of loops, the complexity for each loop can be added such that one might run for O of n, while another loop might have run for O of k. So summation of all these complexity may give us the worst case as O of n plus k. Here you can see an even more linear function when n is enlarged to 10,000. What if the elements are in the range from 1 to n square? We can't use counting sort because counting sort will take O of n square, which is worse than the comparison based sorting algorithm. So is there any other solution? Well, yes, radix sort is the answer. The idea of radix sort is to do digit by digit sort, starting from least significant digit to most significant digit. Radix sort uses a counting sort as a subroutine to sort. Here's a step-by-step implementation of radix sort. First, we find the largest element in the set, and then assign d to be the number of digits of that largest element, because we have to go to all the significant places of all the elements. Now, we have to go to each significant place one by one and use any stable sorting technique, most preferably a counting sort, to sort the digit at each significant place. The following example might help you understand about radix sort a bit more.
Radix sort is used on a large range of values. We'll first sort using a stable algorithm. The last number, if we sort using this, we'll get this array. We'll use the second last number. So for example here, the 3 is the smallest integer, then 4, then 4, and so on. Lastly, we'll sort using the third integer, the third last integer here. Since there is no integer here, we'll assume it's a 0, and we'll sort others like this. So after 0, there is 1, then 2, and so on. This is how radix sort works.
Similar to counting sort, we have also implemented radix sort using Python. This algorithm is very similar to the counting sort algorithm. The only difference is the external loop while. We're going to run this algorithm on a temporary list given below. The result is a sorted list of n elements. To visualize the performance of our algorithm, we can run this algorithm for different lists. Here, we are running our algorithm for many list sizes up to 100. You can see here that the relationship is almost linear. Here is a snippet of our Python code drawn for elements having size of up to 800. For Radix sort that uses count sort as an intermediate stable sort, the time complexity O of d into n plus k. Here d is the number cycle and O of n plus k is the time complexity of the counting sort. Thus the Radix sort has a linear time complexity which is better than O of n log n of comparative sorting algorithms. Now finally discussing bucket sort. Bucket sort is a sorting technique that sorts the element by first dividing the elements into several groups called buckets. The elements inside each bucket are sorted using any of the suitable sorting algorithms or recursively calling the same algorithm. Several buckets are created. Each bucket is filled with a specific range of elements. The elements inside the bucket are sorted using any other algorithm. Finally, the elements of the bucket are gathered to get the sorted array, as can be seen in the example that's coming up next.
Bucket sort is used when we have a smaller range of values. The bucket ranges from point 0.1 to point 0.7. This range of values can be seen from the list. The interval of each bucket is point 0.1. When you traverse through the list, each value is inserted to the bucket corresponding to its range. Since we are sorting in an ascending order, the values of the first bucket will come first, and so on. This is how the algorithm of the bucket sort works.
Similarly, we have implemented a bucket sort algorithm using Python. In this algorithm, the number of buckets created are equal to the length of the list, and the numbers that fall into a specified range of the bucket are divided into the buckets that have been created. These buckets are later sorted and then concatenated back to again to form the original list, keeping in mind that the original values in the list are very small. Sort the given list using the bucket sort algorithm. As you can see, the bucket sort has sorted out an unsorted list. The performance of the bucket solve algorithm. We will run this algorithms n times, given that each time the value of n that corresponds to the size of the list would increase up to 1000. Running this algorithm, we get the following result. As you can see, this nearly satisfied a linear relation. Here's a snippet of the Python code for the R bucket sorter. Here you can see the graph behaves even more like a linear function when the value of n has been increased from 1000 to 10,000. The worst case complexity of bucket sort is O of n squared. As when there are elements of close range in the array, they are likely to be placed in the same bucket. This may result in some buckets having more number of elements than the other. It makes the complexity depend on sorting algorithm used to sort the elements of the bucket. The complexity becomes even worse when the elements are in reverse order. If insertion sort is used to sort the elements of the bucket, then the time complexity, the best case complexity is O of n plus k. It occurs when the elements are uniformly distributed in buckets, with a nearly equal number of elements in each bucket. The complexity becomes even better if the elements inside the buckets are already sorted. O of n is the complexity of making the buckets, and O of k is the complexity for sorting the elements of the buckets using algorithm having linear time complexity at the best. case. The average case complexity is O of n. It occurs when the elements are distributed randomly in the array. Even if the elements are not distributed uniformly, bucket sort runs in linear time. It holds true until the sum of squares of the bucket sizes is linear in the total number of the elements.